Rather than modes of modulation that we've been hearing about earlier on today, I'm going to talk about a mode of propagation, something that's interested me for the last 4 or 5 years. I've been licensed for over 40 years now. I first became aware of meteors as something to do with radio. Incidentally, while we're talking, I've got a piece of meteorite to hand around that you might like to have a little look at. Back in the UK in the 1970s, I built some 70 meg 4 meter equipment, all using valves, and there was one beacon on in the UK at that time, and I could just hear this thing on the edge of what I could hear. And I was aware that just every now and again this tiny little signal used to leap out of the noise just for a split second. And I investigated and from others discovered that this was about meteors. But didn't think that, I thought this was just some anomaly, nothing to do with communication and not much use. The first time I became aware that meteor scatter could be used for anything useful for radio communication was as one of the members of the VK4UH VHF expedition out to Norfolk Island a number of years ago, when meteor scatter was being used for communication, and I was absolutely spellbound from then on. Now, if you've only used 2 meters as an FM channel, as a telephone from the car through a repeater or whatever you like, and it's very good for that, you're only really just scratching the surface of what 2 meters and the VHF bands are capable of doing, because that normal 30-kilometer range of distance that you'd normally expect, on some days it can be several tens of kilometers, hundreds or even thousands of kilometers of path can open up for you. And that, of course, is part of the real magic of the VHF bands. Now, normally when 2 meters, and we'll start off talking about 2 meters, opens up to long distance DX, it's usually due to either tropospheric ducting or tropo, where ducts form in warm, still air, so a summertime phenomenon, and our waves propagate between 2 layers of warm air high in the atmosphere, or even low down near the ground, but for thousands of kilometers with very low attenuation. The other mode of propagation that often gives very long distances is sporadic E. Again, a summertime phenomenon, sporadic E, when there's such intense ionization up in the E layer that it even supports reflection of VHF signals. There are other things, satellites obviously. If there's a man-made satellite up there, you can reflect or retransmit your signal, and if the satellite's in your line of sight, whatever the satellite can see is then your field of play. And the extreme for weak signal stuff, I suppose, is EME, moon bounce, where you use the moon as a passive reflector to bend your signal around, and 2 meter signals and way above 2 meters can easily get around to the other side of the world. You can work into the USA, you can work into South America, North America, Russia, etc. The mode I'm going to talk about today, though, is meteor scatter. And just right to start with, I'm going to just define a few terms. What is a meteor and what is a meteorite? Okay, this is a meteor. This is what we've all seen. Anybody who's been outside in the evening time has probably seen one of these, a shooting star or a falling star, a wishing star if you will. It's a brilliant flash of light that can traverse for thousands or hundreds of kilometers across the sky, sometimes several degrees of arc, much brighter than the surrounding stars, but only lasts for a tiny blink of a second. And these wishing stars have been given magical significance for centuries, and if you wish on a wishing star, then who knows if you're actually going to get what you're wishing for. Now, a meteorite is something quite different, and I've passed around a piece of meteorite for you all to have a look at. Meteorite is a piece of extraterrestrial material that's reached all the way to the ground. So a meteor has to burn up on re-entry, and that's the cause of the flash that we'll talk about. Meteorite, it has to get to the ground. Extra come from other parts of the solar system or other parts of the cosmos. So a meteorite actually has to get to the ground. This is a picture of a meteorite that's actually on display in the Smithsonian Museum in the US. It's many meters tall. You can see it has a very smooth outer surface and looks metallic because it is. Most meteorite is composed of nickel and iron and silica. And inside that you'll see large spaces, and these would, when this was in air, this would have been filled with ice, either frozen water or frozen methane. And if you ever came across a meteorite of this size, there's not much danger that you're going to get burnt, as all the movies would have, but you're probably going to get frostbite because it'll be absolutely just above absolute zero. So the process of meteor scatter propagation relies on meteors, these are the ones that are burnt up, actually getting ablated or completely evaporated as they enter into the Earth's atmosphere. So tiny fragments of rock get accelerated into the Earth's gravitational field. They pick up enormous kinetic energy. The first bit of the atmosphere where there's enough resistive force to slow them down and dissipate that energy is at around about 100 kilometers above the Earth. And 100 kilometers, you'll remember, that is actually the height of the E layer. And in fact, the very existence of the E layer is at least in part due to the bits and pieces of metallic iron that's been dropped in and evaporated up there in the E layer. So the bright flash that you see optically with meteors is not due to the meteor at all, and the reflections that we get in meteor scatter are not due to reflecting signals off the meteor itself. That's far too small, there's not enough mass there. It's not even the debris left behind the evaporating meteor. What's actually lighting up and what causes the reflections is the column of air that's being compressed in front of this fraction of dust that's at enormous hypervelocity. And the air gets so heated and so compressed that it becomes incandescent, lights up, and it gets so hot that electrons are actually blasted out of the outer shells of the molecules of gas up there in the high atmosphere. And those free electrons are actually the cause of the reflection. So the more electrons that are released up there, the higher the density of electrons, the more reflections can occur, the longer the ionization will persist, and the higher the frequency that can be reflected back down to Earth. So as we've said, the flash is due to superheated air releasing free electrons, and there are two types of return or echo that we're interested in if you use meteor scatter for communication. The vast majority of reflections, or returns, are what we call pings. These are very short, less than half a second of reflection, and these come from fairly small fragments of dust burning up. Longer periods sometimes occur, and these are less frequent, and they're called burns, and the ionization left behind the ablation of a large meteor can actually give you propagation that goes on for 20 or 30 seconds, or sometimes for minutes at a time. The reflections that occur actually have some quite characteristic features. And talking first about the ping, now ping is, as I said, is a very short reflection. There's a very, very sharp rise time in the signal that you receive at the ground, and then an exponential decay, and the whole business taking less than usually 0.1 of a second. So 100 milliseconds is a typical ping. With the burns, you get a single rise in amplitude, but then it continues to rise, and it can persist the ionization for long periods of times, tens or hundreds of seconds, and it's characterized by these often deep fluctuating signals, rather like you get when you use aircraft enhancement, and for the same reason there's alternating periods of subtraction and addition of waves coming from multiple parts of that ionized trail. Now, as we've said, meteors are being ablated at the E layer up at about 100 kilometers. Here's a photograph taken from the International Space Station looking down on Earth, and you can see out here that there's a meteor trail. It's probably 100 kilometers long, and it's about 300 kilometers below the space station. The space station's up at about an altitude of about 400 kilometers. So when do these meteors come? Well, there's two types that we want to talk about. First of all, we'll talk about random meteors. These are the ones that occur every day, and all hours and every day of the year. And as I said, they do come every single day of the year. And then there are meteor showers, and these are periods of time during the year when there's an enormous increase in the amount of meteor activity, And even from the optical days, these have been recognized for centuries, is that at certain dates in the year, we expect to see meteor showers when there can be hundreds or sometimes thousands of meteors coming down. So let's talk about random meteors first of all. As I've said, they come every hour of the day and they come every day of the year. There is, however, a peak of usable meteors, the ones that we can use for communication, that occurs just before dawn. And then there's a corresponding lull that occurs in the afternoon. There's a peak that occurs during the spring seasons of the year and a corresponding lull that occurs during the autumn or vernal seasons. Now the size of rocks that we're interested in for propagation at 2 meters are particles of dust that are somewhere between 0.1 of a gram and about a gram. So we're talking about something that's somewhere between the size of a grain of sand and the size of a dried pea. This is the sort of thing that we're looking at. And to achieve to actually become ablated and cause those ionized trails, they have to be running at somewhere between 10 and 100 kilometers per second. Now you note that this is kilometers per second, not meters per second. And from your school physics, you'll remember that kinetic energy is proportional to the velocity squared. If you increase the velocity of something by a factor of 10, its energy goes up by a factor of 100. And if you go up by a factor of 1,000, then you've got a million times more energy has to be dissipated when you slow these particles down. This is a depiction of a woodcut that's on display in the Louvre in Paris, and it depicts the Leonid meteor shower in 1833, which was so intense, where there were thousands of meteors an hour were seen to come to Earth, and it caused widespread panic all across Europe because they thought it was the first sign of impending doom, the falling sky. Now the other interesting thing about meteor showers is that when you get meteor showers, all of the meteors appear to be coming from the same place in the sky. This is a time-lapse photograph of the constellation of Orion. Now, after the Southern Cross, the constellation of Orion is probably the easiest constellation to recognize. That's the Hunter, and it's the 3 little stars in his belt. Everybody's seen Orion, I'm sure. He's upside down in the southern hemisphere, and the bright star is his sword. But you'll see that all of these individual meteors that have occurred over a number of hours all appear to be coming from here, right in the middle of the constellation. So the constellations have been named historically depending on the meteor showers have been named by the constellation from where they appear to be coming. Of course, the meteors are not coming from the stars at all. They're thousands of light years away generally. It only occurs because meteor showers occur when the orbit of the Earth around the Sun takes it through clouds of gas and debris that have been left behind after a comet has come through the solar system. So the comet comes through, leaves a big trail of crap all the way behind it, and we go through that pile of crap on the same date every year because our date is determined by where in the orbit around the Sun we are. The constellations appear for the same reason, and so that's why they appear to be coming from the same place in the sky. Now, meteor showers are very useful because there's so many more meteors around to do propagation, and there are 11 major meteor showers every year, so there's almost one a month. And in the better of those, you can get tens or hundreds of meteor returns an hour. I've listed out the major 6 that we use for 2 meter propagation. The big 2 are the Aquarids from the constellation of Aquarius, which was just 2 weeks ago and was pretty active this year, and then the Geminids, which occurs around Christmas time. So how much material, this extraterrestrial material, do you reckon comes into the Earth's atmosphere every year? Well, even the most conservative estimates reckon somewhere between 100 and 150,000 tons of material come into the atmosphere every year. And if you divide 100,000 tons by the weight of a grain of sand, that gives you roughly an idea how common meteors really are. Okay, so you might say, all right, here we go. So I'm going to get a signal on 2 meters from 2,000 kilometers away for a fraction of a second. How am I going to get a QSO out of that? Now, in the 1960s and 70s, the only way that could be done was by the use of high-speed CW. Bear in mind, home computers at that time were pretty much in their infancy, but we did have electronic keyers that could get up to 1,000 characters per minute. So a string with a call sign and a report would be blasted out for a set period of time, and at the other end it was recorded on a huge multi-speed reel-to-read tape recorder, and then after the event it was slowed right down to try and decode what the message was. That was the area of the real super geek, of course. So in the 1960s, mostly valve equipment, no computers. Some electronic keys would transmit for you, but two useful things came out of this time. The first was that the concept that the only way of using Meteor scatter is that the two stations have to transmit for long periods of time and keep repeating the same message until it gets through. And they also was responsible for the two-letter reporting system that's still used today for Meteor scatter. I'm going to move along a little bit because we've covered a lot of stuff already in the previous talks. Now that all changed dramatically in 2001 because of this guy, Joe Taylor, who you've already heard discussed today. Joe, or Emeritus Professor of Physics at Princeton University. He's a Nobel Prize winner. He got his Nobel Prize for identifying pulsars, the radio stars, but he's also a radio ham K1JT. And in 2001, he gave to the amateur community a whole suite of software to help us use a number of esoteric different modes of propagation and for weak signal work. So WSJ was weak signal Joe Taylor, and they're all based on the principle of using a computer to do all the legwork. Okay, so all of the systems that Joe Taylor and most of the digital work that we still do relates to using audio tones generated by a computer stuck into a single sideband transmitter. And as you know, if you put a single audio tone into an SSB rig, you get a single audio carrier out. And if you wobble and move that tone around, then the RF frequency follows it up and down. So you use audio frequency shift keying. You put audio in, you get RF encoding out. The incoming carriers are converted back to audio, and the computer does all the work and does all the decoding. Now, WSJT, it was discussed a little bit earlier on. The latest versions of this are still around, but there were two major modes that are of interest to us. JT65, one of the original modes, was set up for EME work. It used a very slow method of modulation and a long period of transmission. And this turned EME from the province of the superstation with the massive dishes and massive power and lots of real estate and money down to something that you can do from your own backyard. And probably several people here I know have done EME using this with fairly modest equipment. Now JT65, as Rex touched on earlier on, has also found a place for weak signal HF work. So you can use very low signal, very low power levels to communicate over great distances. This is a slow mode. You're transmitting a very slow modulation rate for a long period of time. The other mode, and the one that's of interest to us today, is VK4UH. And if I'd been giving this talk just 6 months ago, this would still have been the mainstay of digital Meteor scatter operation in VK. Things have changed, and we'll discuss that because there's been some new developments in the last few months. If we understand the principles, though, what FSK441 did and how we use it, that applies to all of the new modes anyway. So FSK, frequency shift keying, 441, basically it used 4 discrete audio tones, all within the passband of an unmodified SSB radio, and the program will transmit one of these tones at any time. So you're key down, but you're just sending one of 4 tones and therefore one of 4 carriers. And it ran at 41 baud. It had a 43 character alphabet, that's all of the letters, all the numbers, and a couple of the extra characters. And because of the way it's set up at that baud rate, it requires 2.3 milliseconds to get each character through. And so the whole point of doing this fast mode was that you have to get your message through in that 100 millisecond ping. Okay, so this is a fast mode. It's not a weak signal mode, it's just a very short signal mode. And like all of these things, it relies on enormous repetition. So you send the same tiny little message over and over again, thousands of times, and eventually it's going to get through because the meteor is going to come in at that time and the signal will get through. So FSK441 used a string or a message of 23 characters, which is enough for 2 call signs, a grid square or a report, and it's something that you know you can get through in the 100 milliseconds, which is what you're going to get from a ping. And the idea is that the 2 stations basically divide the minutes, the time, into 2. You transmit for 30 seconds, you receive, the other station receives, and then at 30 seconds you swap over. So you can see that it requires a fair amount of time locking to be able to do that, but not as accurately as many of the other digital modes. So FSK441 divides each minute into 2 periods. The first period from the top of the clock down to 30 seconds, and the second period from 30 seconds back up to the top of the minute. As I've touched on, FSK441 has almost been relegated to an heirloom mode now. There are two current pretenders to the throne, MSK144, MSK-MS. I'm not going to say too much more about this because there isn't time, other than to say that they're forward error correcting modes. So rather than getting the message you want in gobbledygook at either end when the decoders can't get it anymore, with both of these modes, you either get the complete signal the complete message as it was sent, or you don't get anything. But because of the improvements in the encoding, it allows us to get reliable decodes and pings that are substantially shorter than the 100 milliseconds, which was the best that the original software could do. So good, in fact, that we've now, like FT8 that we heard about, we've switched to using 15-second periods rather than 30, which is a lot less hard work for the PAs, I can assure you. This was also touched on in earlier talks. What do you actually need to constitute a QSO? What actually is a contact? And this is already being predetermined and agreed. Basically, a QSO requires you with your other station to exchange call signs, and it requires you to exchange a piece of information that you can't predict. And generally that's covered by a signal report in both directions. And because you're trying to work another station, it's all very well getting the signals through, but you have to have some way of confirming that all the stations have got everything they need. And the way that's normally done, and it's been done since the days of high-speed CW, is with a two-digit report. The first of the 2 digits goes from 0 to 3 and gives you an idea of the duration of the ping that you've received. Anything between 100 milliseconds and a second is a 2, and anything was from 0 to 10 dB above noise is a 6. So the commonest report that you'd ever get would either be a 2.6 or a 2.7, and that's roughly equivalent to a 5 or 9 in SSB, and that's what you mostly see. How does a QSO run? Well, pretty much as you see here, and I won't go into any detail on this. Most contacts start with a CQ, and so here it's me calling CQ with my grid square, and I would continue to transmit that every 30 seconds until I get a response. Eventually somebody's going to receive that bounced off a Meteor trail. In this case it's Ari down in Melbourne. He's picked me up, so he sends me a report, VK4UH stroke 2.6. The stroke told me that that 2.6 was associated with me, and if there was nothing at either end, that's the originating station. Once the 2.6 is received, the response is an R26, like in EME. R means Roger, I've got my report, and my report to you is 2.6. And when all that's gone through, the next report is RRR. Roger, 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 I've received all the information I need, and the QSO is actually complete. But of course, I don't know that, or rather he doesn't know that, and I will continue to send that until I get a 73 comes back through from the other end, just to complete, and then both stations can go on and try and work somebody else. So how far can you actually work with Meteor scatter? What's it going to do for you? So here in this image, what I've done, I've overlaid the map of Australia with 2 concentric circles, both based up here in Queensland on Brisbane. Now the red circle is out at 1,000 kilometres, what I would call the easy zone, and the blue line is out at 2,000 kilometres, which is the limit of what Meteor scatter can actually do for you. Because of the geometry of the curvature of the Earth and the height of the E layer, at the 100 kilometres height, even signals that are taking off at 0 elevation and being received at elevation, the maximum distance that you can work is around about just over 2,000 kilometers. Now, the best reflections of all occur when the Meteor trail crosses at 90 degrees to the path between the two stations. The loudest response comes when that is as close as possible to the middle of the track between the two stations. So out here in the red zone, there are lots and lots of possibilities, lots of meteors in all sorts of directions that they can come in, and you'll still be able to get the pings through. As you go beyond out to the limit, it becomes progressively more difficult. The signals become weaker, they become less frequent, and by the time you're out at the blue line, the meteor has to cross exactly the midpoint of the path between the two stations and exactly at 90 degrees. So once you're out here, it starts to get pretty tricky. So you can see that from Brisbane, inside the red zone, I can get into New South Wales, I can get into VK1, I can get to VK3, I can get to VK5. Inside that blue zone, I can also get to VK7, but from Brisbane, most of the New Zealand major cities are not attainable. They're just too far away. If you live in Sydney, you can work New Zealand every day of the week on Meteor Scatter. Now, these images were supposed to be graphic, and unfortunately they're not working on this computer. They're just to show, though, that the screen is, unlike FT8, which we saw before, they also use a waterfall display. You know, most waterfalls have frequency across the top. They track down in time, and the intensity of the signal lights up on the screen either as a splat or a different color. When we use Meteor Scatter, we turn it on its side, so it actually runs left to right in time, low frequencies at the bottom, high frequencies at the top, and the yellow line here is an S-meter trail. So you can see that there's a ping at this point. It should have graphically run across now, but I can't make it work. So you can see that there's a ping, you can see that it appears in the S-meter, and it appears on the screen. And in fact, you can often hear these pings in the loudspeaker quite clearly. Here is a burn. This one you can see, this one you can see extends for almost 15 seconds, probably into the next receive period as well, much higher amplitude. And up here on the other screen is what's been decoded from that. In this case, it's Colin down in Mount Gambier, VK5DK calling CQ. So that's what a burn sounds like. And that seems to go on forever when you hear these come through on the speaker. I can't show you anything in that because I can't make it run. Now, when I started doing Meteor Scatter at the end of the activity sessions, we used to have a 40-meter net so everybody could describe who they worked. That's been overtaken these days by the use of the VK logger, and most people will post up when a contact is complete, and also the process throws up a graph to show all the different contacts that have been made. So when do we do Meteor Scatter operating? Well, you can do it any day of the week, but there are two distinct activity sessions that are set up in Australia to try and get us all the opportunity to work as many stations as possible on 2 meters. They run on Saturday and Sunday mornings, and because of that pre-dawn peak, they're generally set up to start just before dawn. So normally from about 7 o'clock in Sydney and Melbourne, certainly through the winter time. The operating periods run for 1 or 2 hours until propagation starts to die out, and everybody operates on the same frequency, exactly on the same frequency, not even spread out a little bit like in FT8. So on 2 meters, the primary frequency is 144.230, and on 6 meters it's 50.230. Now, obviously, if you're operating in alternate periods with your partner stations, the primary thing that you have to do is that you have to be in the other period from the guy you're trying to work. I mean, that's pretty common sense. If you're not transmitting when he's listening and vice versa, you're never going to make a contact. The other thing, though, because you're all on the same frequency, and there might be 10 stations in Brisbane all transmitting together, the other thing that you have to have is that you have to be in the same period as everybody that's in local range of you, because otherwise you're just going to be completely blasted out of existence by the very strong local signals. So there's a protocol that's been set up to guide the stations into which period they should be operating on, and set up so that everybody gets the best chance of working as many as possible. And the principle runs that those of us up here in the north, up here in VK4, we always transmit in the second period and we always beam south. Stations down in the southern states, VK3, 5 and 7, they do the opposite. They always transmit in the first period and they always beam north. So you can see that you can work between north and south. The guys in the middle, so the guys down in VK2 and VK1, they change depending on which day of the week it is. So on a Saturday morning, they join the northern stations, they beam south and they run second, and on Sunday mornings they flick over and they run first and beam towards the south. Okay? So you might say, well, that's all very well, but if I'm in Hobart, how do I work the station in Melbourne? And the answer is, well, clearly you can't, or you can't do it, or at least you can't do it during these operating sessions, or you can't do it on the same frequency as everybody else because there's no way of doing it. Same applies if you're in Canberra and you want to work, and it's Saturday, and you want to work Brisbane. How do you do it? Well, you come back tomorrow, because tomorrow on Sunday you're going to be beaming north, and you'll be able to do that. So, although it's not perfect, it allows the best chance. I mean, working from Hobart to Melbourne, there's no big deal anyway. You'd be doing that without the use of meteors. Generally, because 2 meter meteor scatter activity dies out before 6 meters, those stations that run both bands, they start off on 2, and when the propagation starts to fail, they'll click across to 6. Now, what do you need if you want to set up a meteor scatter station? First thing you need is just basically a VHF SSB radio, and just about anything will do. The requirements for frequency accuracy and stability are pretty modest. By the very nature of meteor reflections, a lot of Dopplers involved, you can easily decode stations that are 200 or 300 hertz off frequency further away than you could comfortably copy SSB for sure. So it doesn't need to be all that accurate. Second thing, you're going to need some sort of computer to run your software for you. Just about anything will do. The computing requirements of WSJT and the new modes are very modest. Just about anything that was built in the last 10 years will do, and just about any operating system that's still supported will also be fine. You're also going to need some way of getting your audio signals in and out of the radio. Now, there's lots of ways this can be done. Just about any digital mode that's been used, whether it's computer-generated packet or slow-scan TV or FT8, will allow you to do the same things. Plenty of homebrew options, and there's some commercial ones as well. I use one of these signal links. That's basically a USB outboard sound card plugged straight into a USB port on the computer. But what it does, it makes sure that you've got all the audio levels at the right pitch, so you're not going to overload anything and overdrive your transmitter. It prevents setup so you don't get hum loops or you don't get RF interference, and it also has to drive the PTT, of course, to command the rig to go into transmit. If you've got some of the later rigs, most of the current generations of ICOMs and Kenwoods are quite capable of doing this. They have sound cards built in. This 7851 that I use on 6 meter meteor scatter, that with a single USB cable, no adapters, no level adjustment, does audio in, audio out, PTT and cat control the frequency just with a single cable. It's good to have a bit of power. This isn't a weak signal mode, but it's a very high duty cycle mode. And although you can do meteor scatter with 5 watts, it's pretty hard going. It's hard going for the people at the other end. 100 would be better. The legal limit for digital work on VHF in VK is 120 watts, but you can get a high power permit if you want to, and it's one of the things that's accepted as an application for high power. If you have a 100 watt SSB rig and you try and run it key down 100 watts of carrier for long periods of time, it's going to get very unhappy very quickly. It's going to overheat and drift, and an intermediate amplifier is quite a good thing to do just to take all the strain out of the system. And antennas, well, what do you need antenna-wise? This is a picture of my tower here. I've got a 12-element Yagi, which is probably too big. It's probably bigger than is optimum for meteor scatter. 8 elements would probably be closer to optimum. bear in mind that the signals that you receive off meteor trails don't necessarily come directly in the direction of the station you're working. In fact, statistically, they're more likely to come from what we call the hotspots that are either side of the direct path. There's a hotspot A and a hotspot B on either side. Statistically, which one of those hotspots gives you more signal depends on the time of the day and the season and the path length. WSJT, the software, tells you which one to use. If it knows the grid square of the guy at the other end, it'll actually tell you which is the hotspot to use. And you don't need elevation control like you do with satellites, so you don't actually need anything more than a pretty standard competition grade sideband station for terrestrial work to do meteor scatter. And the final thing that you do need, though, is some sort of time control. Easy to do. There's plenty of internet options for setting your computer clock. Within a second is probably okay. One, so that you get the maximum possible chance of getting the signals from the other end, and two, so you don't deafen all your neighbours, because if you come on early or late, you're going to give them a right caning with an earful of your local signal. Okay, you might say, well, no, that's still not going to work. Okay, we've got 10 stations in Brisbane, 10 stations in Melbourne, all transmitting or receiving together. A meteor comes in, all I'm going to get is 10 stations from the other end, all one on top of the other. How is that going to help me and get a QSO? In fact, it does work, and it works because of this phenomenon of geospecificity, and because of time, it's not all that easy to run through all this, other than to say that the geometry that's required for these reflections to get the signals through is very sharp. So you can have two stations in Melbourne, 1,500 kilometres away, that are only a few tens of kilometres apart, and they don't overlap. Sometimes you get station A, sometimes you get station B. Often you get both of them, but they're separated out in time because of the slight difference in path length and because of this phenomenon of the track actually moving and interference, which we haven't got time to go into all. But just to know that stations do get spread out, and they don't all just appear like a flashbulb going off and everybody's on top of one and another. Why are there only meteors at dawn? Well, there aren't only meteors at dawn. Meteors are there every day of the, every hour and day of the week. But I'll try and explain why we get this peak of usable meteors just before the dawn period. So we're the Earth in the blue arrow, when we're running around on the racetrack around the Sun. It takes 365 days to go around. If you imagine that, it's a rather busy slide, but if you imagine that this is the Earth and we're looking down on it from the North Pole, the Sun's up here and we're looking down on the Sun. Now, the Earth itself is rotating around its own axis, okay, and it goes around once in 24 hours. Now, from the point of view of somebody standing on the surface of the Earth, that equator, if you like, is actually rotating at a speed of about 35 kilometers per second relative to the surrounding space. So we're rotating around there at 35 kilometers per second. The Earth itself, though, is rotating around the Sun, and it takes 365 days to go around the entire orbit, and the effect of that motion is that along this arc, the Earth is moving relative to the Sun at about 30 kilometers per second just because of that rotation. So at this part of the Earth, in the dawn side, those two velocities are going in the same direction. So they get added together. So from a point of view of somebody standing here on the Earth, it's whizzing through space at around about 60 kilometers per second, not far away from the velocity that we need to achieve for the meteors to burn up. They're being drawn into the atmosphere from above. They're spiraling around the Earth and meeting the Earth coming the other way like the bugs on the windscreen. And so they get ablated, burnt up completely, get the reflection. So this is what happens before dawn. The other side, there's only a relative velocity of about 5 kilometers per second here, and what meteors come in often don't reach the velocity that's required to ablate. It's rather like not getting bugs banging into your back windscreen. That doesn't happen. They all hit the front windscreen. Now, what happens if you go to other frequencies? Well, we know from physics that the duration of the ping, the return that we get, is proportional to the wavelength squared. That comes from physics. We don't need to go into it here. So when you go from 2 meters to 70 centimeters, you've reduced your wavelength by a factor of 3. So you're a third of the wavelength, and a third by a third is a ninth. So you know that the ping is only going to be about a 1/9 of the duration. So a 10-second ping on 2 meters is going to be about a 1-second ping on 70 centimeters. The signal strength is proportional to the wavelength to the third power cubed. So that's a third times a third times a third, or a 27th of the signal return. So that's going to be about 15 dB weaker than it would be on 2 meters over the same path from the same meteor. Now I'm particularly proud of this slide. Back in the in the Aquarids meteor shower a few years ago, with ARRI VK4UH down in Melbourne, we set up 2 stations running simultaneously right through the night. One on 2 meters and one on 70 centimeters. So 2 radios, 2 amplifiers, 2 beams, 2 computers, and we recorded simultaneously. Now during the shower, there was a burn on this lower 2-meter trace, and it went on for a full 30 seconds and probably continued beyond that. And coinciding with that burn, here in the 70 centimeter return, is this tiny fraction of a second ping. Okay, so it was still quite loud and we still could make a contact with that, but it just shows this is for over the same path between the same stations, just on 2 different bands on the same rock. So it just shows that as you go up in frequency, it gets very, very difficult. If you go in the other direction, you go from 2 meters down to 6 meters, now the wavelength is tripled pretty much, and so the opposite effect occurs. Now the pings are 9 times the duration you expect on 2 meters, and the signal strength goes up by a factor of 27, or about 15 dB. Here's a typical 6-meter ping, and you can see it spreads right across at a high intensity. These can often be sufficiently long that you can have an SSB. You can have both sides of an SSB contact on one ping. So seeing as the feature of the conference today is what do we do next, what else is of interest, there are these new modes that I've said that have come up and are replacing FSK441. These 2 error correcting modes, unfortunately they're not compatible with each other, so we've got another Betamax versus VHS argument going on. My personal preference is this one, MSK-MS, because it retains that 2-digit reporting system of both amplitude and duration of ping, which gives more information about what conditions are like. MSK144, which has come from Joe Taylor's suite, that only gives a signal report as a number of dBs above noise. Which one will win? I can't tell you. Let's see which way everybody performs. There's also a lot of interest in meteor scatter when it's combined with other modes of propagation. As I said, from Brisbane it's almost impossible to work on meteor scatter alone over to New Zealand, but I've had many contacts to New Zealand, but only when it's being combined with other modes of propagation as well. Commonest one is where meteor scatter and tropoducting occur at the same time. Not enough tropo so that you can get a signal through all the way, but the tropo fills in the path at one end or the other, and the same can occur with sporadic E when it occurs in the gap that meteor scatter can't make. There's also some interest in meteor scatter when it's combined with transequatorial propagation, which gives the possibility of very, very long distances. We still use TEP if you worked on 6 meters into Japan, for example, that's the mode of propagation you basically used. It's the double caudal hop thing across the equator. We use the Chinese video transmitters still as propagation predictors. When you start to see the Chinese TV signals coming up, you know that things are going to work. Often before they appear, you start to see meteor pings appearing because the meteors are filling in the gap that the TEP can't achieve. So in conclusion then, meteor scatter is a very viable mode of 2-meter propagation that can give you communication and contacts easily out to 2,000 kilometers every day of the week with simple, straightforward equipment that you've probably already got. It's not a weak signal mode at all, it's just a very short signal mode, and there are spectacular results to be had when there are meteor showers underway. And at that point, I'd thank you for inviting me to speak today, and if there's any questions, I'll happily have a go at answering them.
Did anybody get any things on the track of that Chinese satellite country?
No, now the catch there is that if it gets to the ground, it didn't burn up. No. Nobody got anything of it. It wasn't hot enough. It has to actually, wasn't going quick enough, wasn't hot enough to do it. Yes?
If you're in Adelaide,
Yep.
do you still point your antenna north?
Yes. Well, you point it more or less towards the station you're trying to work.
Yeah, that's what I meant. So if I was looking for Brisbane, that's not north.
No, but I mean, I say north, but it's actually northeast from you, and it's southwest from us. So what will you do when if I'm working VK4UH down in the Barossa on Meteor scatter, I know what his grid square is. WSJT tells me where the hotspot is. It tells me which one to use, and that's where I point my antenna. You don't point your antenna at the meteors. You point the antenna more or less in the direction of the station, in fact, just a bit either side of it, and you're more likely to get your contact. That's why you don't want an antenna that's too sharp, because if it's too sharp, you're going to miss stuff coming in from the sides. You want something that's as broad as a barn door and a compromise between antenna gain and enough aperture to get the signals in.
Given the elevation of your antennas, so you are fixed?
Yes, they're horizontal. I don't use any elevation at all. I think that might be a trick of perspective. No, the antenna's just, the signals you're interested, the longest distance occurs when you're ground scraping, when you're going out at zero elevation, so you only want a horizontal antenna. The only time you might be interested in elevation apart from satellites is if you wanted to work somebody at a very short distance from you. That's probably not the mode of propagation to use anyway. Okay, thank you all very much.